God. So good evening, everyone. I hope everybody's doing fine. And uh, so we'll get started with where we left last time with respect to sequential models. But before that, as usual, I'm going to make a couple of announcements. So I hope everybody can hear me. If not, just let me know. Last time, I think there was some issue with me hearing you guys. Um, in case in case you say something and I don't hear immediately, let me know in chat. Chat is open for me right now. Okay, so quick announcements. I did extend the submission deadline for assignment 3 to Saturday. It's just for those groups, those teams who need a little bit of more time to work on the sequential models. And today we'll see, again, ideas on sequential models. So hopefully that'll, again, reinforce and maybe build more confidence for you to finish up the assignment, okay? So that's about the assignment. Next is about okay, next is about project progress. So we had meetings with each of you in 2 weeks ago, but I do suggest continue working on it every week. To dedicate time between split time, project plan. It's very important, especially given the magnitude of the grade, proportion of the grade for this. And you can certainly keep me and Teng Teng informed on your progress, hurdles, and so on. Okay. Next quick point is about schedule. So we don't have a class next week because of spring break, but but hopefully we'll finish up sequential models today, so that next after the break we'll take up a new topic. I will probably be back to images, and we'll talk about image generation. Okay, so with that, let me come back to assignment 3, since the submission is still for some of you, or actually the actual official deadline has been moved to Saturday. So we will revisit the encoder decoder architecture, especially for the second question that you might have seen. The example code also has attention in it. So we'll look at encoder decoders again today, and of course discuss attention. That's the main topic for the first part. And then we'll talk about also embeddings. So of course, in the assignment, you have to use Globe embeddings. But today, in the second part, hopefully we'll talk about contextual embeddings. In particular, what I call one example set of embeddings are called BERT embeddings. Okay, so BERT, and we'll look at how to use them. Okay, it's all about how to use pre-trained word representations in general, or pre-trained models in general for NLP. So with that, any questions here? Let me share my screen. Yeah, before I actually get back to annotation, I wanted to quickly look at the lecture goals. So let me actually keep that window open. So we were talking about this module number 5, which is about recurrent neural networks, and last time. So the goals were, we went through a lot of details about one particular RNN variant called LSTM, and there's another variant that we just referred to very briefly called GRU, Gated Recurrent Unit. But we went through some details of LSTM and why intuitively maybe it can capture long-term information that might have appeared a few, I guess, time steps ago or a few steps ago that may be relevant for current prediction. Okay, so that's how these LSTMs seem to empirically at least do better than the vanilla RNNs that we saw. Okay, and where we left off last time was about talking about these sequential model applications. And we'll start from there. So we'll revisit, for example, image captioning and so on. And so you should be, one of the goals is for you to be more comfortable with the applications. And of course, assignment 3, you're already seeing translation application. And today we'll actually revisit the translation application quite a bit as a running example. So, and you will see a couple of more examples, okay, in the same direction. The next set of goals, which is still relevant for today's session, is about the topics are about attention. So as I said, attention is a core topic for today. We'll see two types of attention actually, or two variants of attention. So and hopefully by the end of the session, you will be able to explain um, uh, two attention mechanisms, and at least explain the difference between them. So in particular, the first bullet point is saying how you'll be able to at least get a sense of why something called self-attention, which is a novelty with the class of models that we're going to see today called transformers. The self-attention idea is a little bit different from the encoder or the attention idea that we're going to talk about for LSTMs, okay, for RNNs. So hopefully by the end of the session, you'll be able to not just know about these two attention mechanisms, but also know the slight differences between them. Okay. For the transformer architecture, there are some keywords, I would say, to just be able to say what the architecture is. In particular, for example, there's a notion of keys, values, and of course, there's a notion of something called self-attention. So hopefully, by the end of the session, you'll be able to say what are keys, what are values, what are queries in this attention mechanism that we want to capture. Okay. And by the way, this is just a computational block, and these are all extra keywords to describe this computational block. And at the end of the day, this computational block forms a part of a huge neural network, which happens to do really well in NLP. Okay, so that's what a transformer architecture is really, without going into any details about what it is. And similarly, attention, when I keep saying attention is just think of it as a reference to a computational block that somehow fixes some things, and we'll see what things it fixes, and therefore helps perform better in, for example, things like sentiment classification, or even translation, the application that you've been working on in the second question. And in particular, we'll try to do we'll try to go slowly. So we'll also see how to use this a transformer variant called BERT. Okay, and we'll expand it out later. So we'll try to see how to use a BERT model which is pre-trained. Okay, so there's model weights and all that, just like very CNNs. It's a pre-trained model. We can use that to get, again, word embeddings, okay, but in a slightly different way than the word-to-vec and globe embeddings that you've been seeing before, okay? And we'll see how that type of, that type of access to word embeddings, it's a little bit different, and at the same time, that's what enables transfer learning in language processing. Okay, very similar to transfer learning in images. You had a CNN which would learn on ImageNet. The weights are learned using ImageNet, and then you can use it for example, dogs versus cats, or things like that, right? Or even on CIFAR10, you can use a pre-trained model which is trained on ImageNet. So a similar idea, parallel thing happens here, and we'll learn that. Okay. So any questions? So these are the three goals, just to get a sense of where we are heading to in terms of the overall architecture. Just recap, we'll look at examples again, which was towards the end of last session. Then we'll look at examples, and while talking about examples, I'll talk about attention for RNNs. Then we'll switch over to transformers. Within transformers, we'll look at attention and associated ideas, which include keys, values, and queries. And then we'll look at how to use this transformer architecture-based model as a pre-trained model. Okay. Any questions here? Okay. If there are questions, certainly write it on the chat. I just wanted to, again, so it's not in the goals, but I wanted to say why is the sequence of sessions going this way, right? So we started with text, right? So we started with text, and the first key idea while working with text was the idea of embedding, encodings, okay, vector representations for words, and we had seen vector representations for images, right? So we have vector representations for words. Then we said, okay, now we have a way to represent words using numbers, which is literally vector representations or embeddings. Now we also want to capture structure of natural language, which is the sequential order of words, right? If it's English, there's a certain order in which words need to be placed so that the sentence makes sense. So that sequential information was actually one of the, I guess, motivating applications for building our motivating applications for which we motivated RNNs, okay, the new class of models. So we wanted to capture sequential information. And similarly today, at least the second part of today, transformers also help you capture the sequential information. Okay? So in that sense, RNNs and transformers can be used for other sequential, I would say, prediction problems, in general time series problems, but um, just keep that in the back of your mind. So we started with text. We talked about representing symbols or words, which are just not numeric symbols, to words, sorry, to vectors. And then we saw how to capture sequential relationship. Last session we were talking about RNNs. This session, at least after the first few minutes, we're going to talk about how transformers capture sequential information. Okay, so with that, let me switch over to my annotation thing. Okay, so let me put that here. Okay, as I said, if some of the topics introduced today, you will be familiar with because you've been working on assignment 3, and some topics will be new. But at any given point of time, do ask questions on the chat or verbally, and we'll disambiguate whatever is the confusion. Okay, so let's start with the applications, and one application that we've already seen last time, or not just last time, but even 2 sessions ago, was sentence classification, right? So we used a CNN-based sentence classifier. We saw that even before even looking at embeddings. And here, the sentence classification is just, or sentence classification or sentiment analysis, whatever you want to call it. It has a variable length input. A sentence could be of size, has 3 words, could have 300 words. And at the end of the day, you just need to produce a label. Okay, maybe it's a sentiment label, for example, positive or negative, right? So, and the way you do it is just call your RNN block uh, many times, RNN unit many times, and it actually is done under the hood when you have an nn.rnn layer in PyTorch, for example. And given a bunch of inputs, x0 to xt, you just produce a hidden vector, and then you can just do a linear transformation the usual way you do it, do a linear transformation and then a softmax operation to get a distribution over your output classes. Okay, so, and we have seen this, and this is also part of assignment 3. I think most of you have probably done this already. So the next example is image captioning. Okay, so image captioning is a fixed input, a fixed image size, let's say. We are not changing the image size. So fixed input, but variable length output. Okay, so it's the opposite of um, sentence classification. Okay, so we will see, we'll just look at least the high level view of how the blocks are arranged. So here, what we're going to do is just use a CNN and an RNN architecture together. Okay, so and together those two together, uh, generally the CNN part will not be trained. It's a pre-trained network, and the RNN parameters would be trained such that for any new image, you want to get hopefully a description of that image. Okay, and before seeing these architectures, it may seem pretty magical. How do you do that without doing just a lookup, right? Just memorizing that, hey, for this image, this should be the caption. For this other image, this should be the caption. So let's look at how it's done. So as the picture shows here, you basically have an input image, and you pass it through a CNN. So in the red block is a CNN architecture. You pass it through a CNN. What you get is a vector at the end of the CNN, right? An image embedding. Okay, that image embedding is input to the first RNN block. So the first RNN block is slightly modified. So it takes an additional vector as an input rather than if you recall the original RNN, or if you recall conventionally, the RNN block would have, let's say, 2 inputs and 2 outputs. where the previous hidden layer, the previous RNN blocks hidden output will be taken as input, and then the current input, and then two outputs. Generally, it's one output, but you can also have two outputs, one an explicit output vector or an explicit, as well as an explicit hidden vector, right? So that's why you can see that there's two arrows coming out and two arrows going in, right? So the only difference is that at the beginning of time, as in like the first time step, you pass an additional vector, which is the image vector. So all the information is actually captured in that vector, that image vector, and somehow that information has to be transformed every time it passes through the RNN computation blocks, right? Through this to be able to make predictions about the caption for relevant to the image. Okay, so in fact, all the information is at the beginning, right? But of course, when you're trying to predict hat, you also know that maybe I have already predicted straw as the previous word of the caption. Okay, so that's some partial information also being captured. Okay. So to be more, specific in terms of the architecture, let's say we are using VGG16. Then what you do is as we saw before several times, you just drop the last layer or the last couple of layers. Here, just for illustration, we dropped the last couple of layers. Sorry, last layer, which is the 1000 class, which had the output to be 1000 dimensions, which corresponds to the image in its 1000 classes. So we drop that, and that's the image embedding. Okay. And so what we're describing now is just a forward pass. So most of the times, by the way, by this time, everybody should be aware that most of the times when we describe new architectures, whether it's CNN, RNNs, or even today we'll see transformers, we mostly talk about the forward pass first. Okay, how does vectors go through and we get an output? Tuning the parameters of the network is by backpropagation, and we generally don't focus too much on that. We haven't focused too much on that except for the first couple of sessions when we explicitly did backpropagation. So let's look at forward pass for this. Okay, so forward pass, a test image or an image is passed an input. We get the vector embedding, and then we slightly change the first RNN block. Okay, let's say we are using a simple RNN, the vanilla RNN. So we're not really using LSTM. So what happens is you just have an extra linear transformation. Okay, so let's say V is the vector, this image embedding here. Okay, then we're just passing that extra vector at a linear transformation of that, WIH, let's say, is a matrix. This is a matrix. This is a matrix. So so you have the usual previous hidden vector, which could be 0 at the beginning, right? Which it should be 0, and you provide a starting point, generally, for example, a vector corresponding to the start token. Okay, because you need to say the first word you don't know, but you know that we need to start saying something. So a generic token like a start token would be the first input. So the first RNN block will just have 3 inputs. Okay, that's the only change. And we already seen this before. You'll have a Tannish transformation and then the hidden vector. Okay, so that hidden vector, let's call it H naught. Okay, from that hidden vector, you can do generally a fully connected layer or a linear transformation to get a bunch of scores, and you softmax it, and you get a distribution over words. Okay, let's say the distribution over words. This is the distribution over words. Let's say Y naught. Okay, there is a true word. At training time, you know the true word. For example, the true word should be, let's say, straw. Then you can do a cross entropy loss. So you want to compare, right, whether this is comparable to a vector where the straw index is 1 and everything else is 0. Okay, that's exactly done by a cross entropy loss function criteria, where basically you're thinking of this as a classifier where the number of classes is the vocabulary size. Okay, so but at test time, so in the sense that once, if you already have trained the network, these parameters of the RNN, basically those weight matrices, then what you do is once you get this distribution over words, you can sample from it. Okay, so what is sampling? It's basically if you have a distribution, right, a probability mass function, like let's say a distribution for A, B, and C, you draw a sample and you get A or B or C depending on the probability, their weights, right? So you sample. So let's say, and in the sake of illustration, the sample happens to be straw. Okay, it doesn't have to be straw. Okay, it can be some other sample. And also at this point, I can already say that instead of sampling, you can also do something else, which is take the coordinate corresponding to the highest probability value. Maybe it's the most likely word. Okay, that will be a deterministic way to pick a word. Okay, and so maybe that's also straw. So either sample or take the max, or more, I guess, technically correct, it's argmax. Okay. Right. So let's say we got the straw. Straw is the word. Then we have to pass this word as the next input. So by the way, here I'm already assuming that either there's a representation for words, or if not, just there's some default encoding that you're using. Okay. If not, then remember, just like you've seen in assignment 3, some of you have already seen in both questions 1 and 2, you can always use an embedding layer, okay, from scratch. So yeah.
I have a question. So what is the X naught over here when you're starting in the previous slide?
Oh, it's just the vector representation, some numeric representation for the start token. Okay, so just think of it has a customary word, or you can always say, I can always make it zeros, for example, but it's just a vector representation to say, hey, now you need to start producing something. I need to have a precursor to the beginning of the caption, right?
Okay.
So it's just, I wouldn't say it's zeros, because if it's zeros, then that matrix is gone. I mean, yeah, it can also be zeros. It's fine. So
Okay. The
you
size
can.
will be specified by you.
What will
By
be
us.
specified by me?
As in the size will be specified by us. Whatever the size of the embedding that we want to give can be
Oh yeah,
specified.
yeah. The embedding. So start tokens embedding is the same as any other words embedding. So you get to choose that. For example,
Okay.
if you choose as the one-hot encoding, it will be the vocabulary size, right?
Yeah. Okay.
And if it's something else, it will be smaller. Yeah.
Okay, got it.
You
Thank
get to
you.
choose the embedding, or yeah, you get to choose the embedding size, and you've seen this in the previous
Yeah.
in the notebooks, right? Yeah.
Yes. Got it. Thank you.
I mean, and you can also just do it from scratch, or you can preload the embeddings, and that was the attempt with the Glow embeddings that we saw in
Yeah,
question 2.
that's right. Okay, got it. Thank you.
Yeah. So once you have a word, and of course it's embedding, then that's passed as input. H naught, the previous hidden vector's output, is also passed as an input. We get a new hidden vector, and maybe a fully connected transformation to that, fully connected layer transformation, and then again softmax, again a distribution over words, from which again you can sample or take a max, and you get the next word. Okay, so I think I showed this last time, that there's a lot of scribbling on this slide, and in this illustration just happens to be the right word, hat. Um, and then it's passed again through the RNN. What you're trying to do is, at least at test time, you're trying to see when I'll see a specific token. Just a token is just like a special word, like an end token, and then you stop. Okay, stop the sampling. Now, let me also quickly comment on at training time, what do you do? You're not going to do the sampling stuff. At training time, you already have the image and the right caption corresponding to it. So you're not going to do any sampling. You're just going to do whatever distribution you get. You compare it with to the true word that should be there for that, some ones and a bunch of zeros, right? The one-hot encoded representation of which class it should be, right? Or just the index, you pass the index to the right word, depending on the implementation. And then the next location, you just pass the true caption, the first part of the true caption. Okay, you don't care about taking anything from why not. Pass the first part of the true caption, and check that y1 is a distribution of words. Hopefully, this again, you relate it to the second word that should be in the true caption. So at training time, you since you know the caption that should be there, you try to enforce it basically. Okay, while define the loss functions, and also while passing it forward to the next time step of the RN computation. Okay. Whereas at test time, you can't do that. So you don't know what the true caption is. So you given the distribution, you can sample from it to get a word, and therefore you continue your computation. And every time you get to an output, you sample from that to get to the next word. And that was image captioning. You'll see a lot of code bases. So if you have time, explore it. I don't know if anybody's doing this for your project, but so this is an interesting way to go from images to text. Okay, and if you have really a large corpus, it somewhat works. So, so it's quite interesting and new, I guess, new enough model. Um, Next, let's actually come back to language translation. Or in this case, let me start with an example, which is auto reply. It's the same idea. What I want to spend time on is attention. Actually, that's where we are trying to go towards. So this is just going to be a quick recap. And I know some of you have already finished the second question in assignment 3. So this will be a quick recap for you. So auto reply and other applications like translation, summarization, speech transcription. We'll see speech transcription in a second, and question answering. There's all similar problems in the sense that you have a variable length input and a variable length output. Okay, so your input could be 3 words and translated to maybe 4 or 5 words, depending on if it's a different language. Or your input could be 30 words long and an output could be like 2 words long. Okay, so the lengths of the input and output are not um, predetermined, okay, are not fixed. So let's focus on auto reply, and this is we have seen this, right? So given a email, you want to get a response, right? So given this email, you have these suggestions made by one of the I guess companies here, right? So so how do we get there? So we have a variable length input and we have a variable length output. It could be 3 words long, it could be 10 words long output. And let me not spend time on first version at all. Let's directly talk about encoder decoder architecture. So, so what is the encoder decoder architecture? It's just a nomenclature for the same RNN process that we've been doing. So what does RNN do? It given an input of certain length, hi, how are you? Let's say is a message here. You're just gonna create their vector representations, the embeddings, and then you pass it through the RNN. So if it's length 4, you'll get 4 hidden vectors. Let's say h0, h1, h2, h3. Okay, you'll get the hidden vectors and you also get outputs. Now, what you do is only when you finish passing everything in the input, let's say up to you, then you're saying, okay, now I've seen the whole sentence or the whole input message. Now I need to start generating output. Okay. Now, how am I going to generate output? I'm going to again use RNN blocks. Okay. So how am I going to do that? So this hidden, let's say, nth word. Okay. So hi, how are you? And then an end token, a special token which says, hey, now we stopped. Now we need to. So when I say token, just think of it as a word. Okay. So now we need to start producing output. So now at this point, we have a hidden vector. Okay. So now this hidden vector is going to be the starting point for the next set of RNN blocks. Okay. The next set of RNN blocks are given in this red color. And so how and the decoder blocks exactly what we saw it with image captioning. So we have a um, we have this hidden vector. So at this point, we can do a linear transformation and produce the first word. While training time, we can actually compare the first word to the true reply that you want in the training corpus pairs. You will have pairs of emails and the responses, right? And you'll compare with cross entropy laws, for example. And then you will, but ideally you want to get a distribution over words, and then you can sample from it, pass it to this next RNN block, pass the previous hidden output, and then produce the next word, and so on. So what I'm saying is basically that the decoder block is exactly the same as what you saw in the image captioning example. Okay? If you ignore the fact that there's a huge encoder here instead of fixed input, then it's exactly image captioning, right? So that's auto reply. So that's what encoder decoder is just trying to say what's the processing happening in terms of the sequential processing happening when you're looking at just the inputs, and what's the sequential processing when you are incrementally generating the output. Okay. Um, yeah. So now what I want to do is mention a couple of things. I want to get to attention, but before talking about attention, I also want to quickly mention about um, a particular technique called beam search decoding, and that's just a way to fix a problem that I'll show next. Okay, the problem is Yeah. So the problem is basically, let's say we have an input sequence X, okay, or X naught, X1, X2, X3, whatever, X capital T, and we output a distribution. Okay, so we output a, actually, I keep changing the notation. So we output a distribution of over words, over vocabulary, right? And then we can sample a word, or we can take the word with the highest probability. Okay. If you take the output with the highest probability, then we are essentially being what is called greedy. Okay, we're just being myopic or greedy. Okay? It's a technical word used in some other parts of computer science. It just means that, hey, like for example, why should this word be I am, right? So at test time, right? So maybe it just happens that over the distribution of over words in my vocabulary, I am is the word which has the highest probability. Then I'll pick potentially I am if it has the highest probability. And this choice is just called a greedy choice. Okay, it's also called a myopic choice. And why greedy or myopic is because at the end of the day, I am is not my output, right? I am with some extra stuff is my actual response. So, but while choosing I'm not really keeping track of, hey, I need to actually produce extra things, extra words, for example. And maybe with those extra words, I am may not be the best choice. Okay, if I knew what the extra words were, maybe I'm is not the best choice. That would be non-myopic or non-greedy. Okay, and in contrast, if I don't care about what's going to happen next, and I just, hey, pick the best word now, that's maybe, let's say, I am, then that would be just call a greedy approach. Okay. Um, yeah, and so once you, let's say, chose I am, for example, in a greedy way, then given, of course, the input and now the new word that I chose, I am, we output the next word, right? Just the usual two inputs and two outputs, and pick one of the outputs and linear transform it. Let's say the new output again is here. It's fine, okay, right? So it's fine, and this is I am. So again, maybe fine is the word with the highest probability, the highest probability among the distribution over the vocabulary, right? So this is just again example of greedy choice, greedy decision making. So basically, up till we see the, let's say, the end token, or some sort of termination token, we will greedily pick the word with the highest probability at test time, and keep feeding it to the next RNN block, right? We have to feed, for example, we have to feed IM to the next block, we have to feed fine to the next block, and so on, right? That's how we incrementally generate the output. But the problem with being greedy is, as I said, since we are not forward looking, if I make an early mistake, if for the first word somehow it just happens, because of bad training or some bad choice of, the model being bad, that the first word happens to be a very suboptimal choice. Okay, for example, some verb or something. Then it's hard for you to correct it, right? So because now the next word when you're trying to generate, you're already passing that suboptimal word. So the next word could be off, and so you will completely derail in terms of your response. Okay, so this is something that's a con or an issue with greedy decoding. Okay, greedily choosing a response or this variable length output, and we can fix that, and that's one of the ways to fix it. It's a very old idea from signal processing or EE area. It's called beam search decoding. Okay. Um, so any questions with respect to what the issue is before I tell you the a fix, an example fix for this? Okay, so let's look at beam search decoding. So beam search decoding, as the name says, is something to do with decoding, but not in a greedy way. And the word beam search refers to the fact that instead of taking the best word as a best word, or the index with the highest probability, and just feeding it next time, you actually keep track of several candidate words at any given point of time. So what you do is, for example, let's concretize it here in this slide. We are talking about 3 words. Okay, so what we'll do is, given the input, the first word we want to pick is not going to be the word with the highest probability, but the word with the highest probability, the next highest probability, and the next highest probability. So we'll pick 3 words. Okay, so maybe the highest probability is high, and the next highest is yes, and the next highest is please. Okay. So we'll retain all three, and then the next step of decoding will pass. It's as if we have made three copies of our decoder, and we'll pass first time high with the same with the hidden vector and high as the next input, two inputs, hidden vector and yes as the next two inputs, and hidden vector and please as the next two inputs. Okay, and given that, maybe you get these three words. Okay, so why would we get three words? Again, we're going to look at what's the most likely word, next word, second word, most likely, uh, second most likely second word, and third most likely second word. So these are the three words, for example, given please as an input. Similarly, with hi as an input, maybe a comma, maybe how, and maybe what are the three most likely things, and so on. So you keep track of not just the most likely word, but the second most likely and third most likely word. Okay? For example, so you can choose any, you can just choose any number of such um, choices. Instead of three, you can have two or you can have four. But this clearly explodes, right? If I'm trying to search for the fifth word, I already have like three times three times three times three number of choices. Sorry, number of paths of possible responses that I have. So to not have exploding complexity, exploding number of such possible messages, right? What we do is restrict it to maybe just take the k best. Okay, so in the sense that at any given point of time, we just retain the 10 best or 15 best sentences. Okay, doesn't this get too complicated as a question? It's not too complicated in the sense that it seems quite complicated, but this is something that people used to do even before this sequence modeling. In fact, for much of voice recognition. So voice recognition, or sorry, automatic speech recognition systems from 90s, 2000s, which even before deep learning, they would do beam search decoding. So actually, yeah, in statistical signal processing, beam search decoding is a well-known idea in general. Um, so, um, there's another quick question: how do we manage memory? So it's a question of, so you're not copying the model, right? So you're just maintaining, let's say, k best, okay, 10 best sentences. So at any given point of time, you just have to retain, hey, what are the 10 best sentences that are getting formed? Okay, so 10 sentences is like there's certainly a multiplier effect of how much memory you need to retain in terms of like while doing this inference or doing this decoding, but it's not any onerous amount of memory that you're using. Okay. All you're doing is you have a pre-trained model here. We're just trying to decode a given input sentence, given input text. We just want to know what the right response is or the translation is, right? So we just keep track of the top k best sentences or top 10 best sentences. Okay. And this is being not greedy because maybe hi happened to be the best, most likely word, but hi and then what and so on. It may turn out that hi is not the right choice if you actually really look at the, if you want to look at the whole sentence. Okay, so if you look at the 10 best choices, uh, 10 best choices of responses or 10 best sentences starting with hi may not be the right responses. Okay, in the sense that the probability of hi times probability of this guy, whatever, comma times probability of something else. The combined probability, which is just a product of these probabilities, let's say, may actually be lower than some other choice. Please, come to the class or something. That sequence of words may have a different, product of probabilities, right? So there's a way to score these sentences so that you're not being greedy. Okay, greedy would be what's the best word, what's the best word, what's the best word, and done till you see the end token.
Okay. Okay. Got it.
Yeah, just trying to keep a track of, hey, something else which could have been is not the best word but may lead to a good response, basically.
Okay. Got
And
it.
how do you score it is just based on the probabilities of these words that you would anyway know. When you produce predictions, you would have a distribution of words, so you know the words probability at that point of time.
Okay. Got
And
it.
so the quality of a sentence is just a product of the probabilities of the words. Product of the probabilities of the words. Yeah.
Okay. Got it. Yeah.
Yeah, it seems a little bit complicated, but this has become standard these days. So it's worth. I mean, if you have time and if you're doing something like this, like a time series type of problem, then it's worth testing whether greedy versus beam search decoding if there is an improvement in your response. Yeah. just like post processing. It's not really related to the ML model, but it's like trying to deal with the ML model's myopicity, that is only producing one word at a time. So we need, if we can keep track of the k best things, then maybe you know, being greedy, you know, can be fixed. The issues with being greedy can be fixed. Um, yeah, and finally, I want to start with attention, right? So far, you know, it's just something what we discussed so far is the encoder decoder architecture, and hey, let's not be greedy. We could have some variant like beam search decoding to deal with the fact that the variable length output, since we're generating one output at a time, the sequence of outputs may you may be off because you made an early mistake at an early time step. Okay, so that's what we were trying to fix. Next, what we're gonna fix is the fact that in this encoder decoder architecture, all the information passage is happening through a bottleneck vector, okay, a bottleneck vector, and that's this HN vector. Okay, so no, it doesn't matter whether your input email or input sentence has 3 words or 300 words. Everything has to be compressed into maybe 100 dimensional or whatever is the hidden dimension, right? The RNN's hidden dimension size. Let's say it's 100 dimensions. It doesn't matter whether input is three words or 300 words. Everything, all that information has to be compressed into this 100 dimensional vector. Okay, and from that 100 dimensional vector, you need to produce potentially a 3-word response or a 300-word response again, right? So in some sense, that you know, that's like a bottleneck, right? It may not be able to capture all information. Okay, there's some level of information that may be lost because you're only looking at the last hidden output. Okay, and when I said, you know, information will be lost because we're looking at last hidden output, the natural thing to say is that, hey, we have all these hidden vectors. Is there a way to use them while generating these predictions? Right? For example, a naive thing could be, hey, let's use the first hidden output while predicting the first word. Let's use the second hidden output while predicting the second word, and so on. Maybe, right? That's the candidate. But a more, I guess, a more principled approach. I wouldn't say more principled. Yeah, more principled approach. It seems to work well empirically. Is the introduction of an extra, I guess, computational block called an attention block. I'm just interchangeably using it as attention mechanism, and we'll see how, you know, how while generating each of these words sequentially, will not just rely on the last hidden vector, but we'll try to rely on all the previous ones in a somewhat clever way. Okay, so that's what we're going to do now. Um, and since I want to do that, I'll skip speech transcription example, and I think that's pretty much it. Yeah, so I'll skip speech transcription because it's actually just encoder decoder example again. So so let's talk about attention. So for that, I have a different deck. Um, I think it's the same deck. Sorry, I'm going to scroll a bunch of slides here. Um, yeah, so there were a bunch of slides there, but it's basically lecture 5A. Okay, so if you have that link to the lecture slides, it's just 5A, which is I guess the 5 addendum or appendix. So that's what we're going to do. We're going to look at attention. So I hope. So let's jump into it. So what we're going to do, as I said, is you know, somehow deal with this issue that from encoder to decoder, the information is only passed through the last hidden vector that's computed, right? So how do we fix that? We somehow want to use the previous hidden vectors that we've computed, and how do we use the previous hidden vectors? We're going to illustrate through an example. Okay. Now we'll switch back to, instead of auto reply. Auto reply was just a I guess throwaway example. We'll, for much of the rest of this session, we're going to continue talking about translation. So since translation is a part of assignment 3, many of you must be already familiar with it. So we'll look at translation as an example. Okay. So it's again a variable length input, variable length output problem, usual. Okay. So what we're going to do is compute attention scores. Okay. given some function. So let's drop this alpha here. This is not the right notation here. Given some function f. So what do we do? So let's say we have a sentence in this case in this case French. So what this diagram is showing is the hidden vectors. Okay, there are 1, 2, 3, 4 hidden vectors. Okay, and from the hidden vector, I also did the first um, decoder step. Okay, first decoder step, as I need to give a canonical starting, I guess, point so that it generates the first word. In this case, the first translated word. So let's say I gave this, and I've gotten another hidden vector, but inside the decoder part, right? Inside the decoder. I'm not showing the rest of the decoder here. Just think of this huge decoder here. There was a huge encoder here, and huge in the sense that since I have only 4 words, there are four hidden vectors. So what we're going to do is now start computing what a now start talking about how to use attention while generating the first word. So what is the goal here? Let's focus on one step at a time. As usual, we want to generate the first word, right? While generating the first word, the usual procedure would have been, hey, here's your hidden vector, directly transform it like a linear transform it, and you'll get a bunch, you'll get some vector, and then just think of them as scores, normalize them, and you get a distribution over words. Okay, so we're not going to directly connect it here. Okay, directly connect the green dots. Green dots just represent the decoder's hidden state. Okay, let's call it S1. So this is S1, and let's call the hidden states here H1, H2, H3, H4. Hidden states or hidden vectors is all the same thing. Okay. Um, so we have these 4 hidden vectors in this example, and we have one decoded hidden state in this current snapshot. And there will be potentially more later. What we'll do is first, let's say we've been given some function f. Okay, this function takes 2 inputs, 2 vectors, in this case h1 and s1, and produces a scalar number, a single number, 200 or 0.01, I don't know, some vector, some number. Okay, let's call this a11. So why is the index 1 and 1? It's just the index of the h subscript 1 and s subscript 1. H subscript 1 just represents the hey first word in my input. S subscript 1 just represents hey first step of my decoder. Okay, so we produce A11. Okay, this A11 is called an attention score. Okay, so we actually are going to produce, and from this figure you can already see that we may be producing roughly 4 attention scores. Okay, and that's made clear here. So the next attention score is just going to use H2 and S1. So we're just going to use the second vector and produce an attention score A12. Okay. Yeah, so we produce 2 attention scores. Similarly, we can produce 2 more. Okay, so third attention score, A13, and fourth attention score, A14. Okay, so those are the 4 attention scores you can produce. Again, recall, how do we get it? First index is just the first index in the attention score is just saying, hey, at what step of the decoder we are in. We are in the first step, so A1. And attention score A14 just means that this is the score when we're when we're in the first step and we are using the 4th hidden vector. Okay, so this is H4 here, H3 here, H2 here, H1 here. So we have these 4 numbers because we had an input of length 4. If we had an input of length 10, then it will be A1 to A11 to A110. Okay. So we have this hidden attention scores. Now, just like we saw with fully connected layers, there's a scores, so we're just going to transform it into numbers which are between 0 and 1. And how do we do that? We'll apply a softmax transformation. Okay. So let's say the softmax transformation gives us a bunch of numbers which are between 0 and some value 1. So we had 4 numbers. These are numbers, free numbers, right? I think free numbers in the sense that they can be anything, positive, negative, larger than 1, and all that. We're just going to transform them using a softmax operation so that everything is between 0 and 1. Okay, and they all sum to 1. That's the softmax transformation. Now, once we have the softmax transformation, what we'll do is again reuse h1 to h4 in the following way. Okay, so we're going to use, yeah. So before before I talk about the use, let's just call this um, transform number for the first hidden vector. Sorry, for the when we're talking about the first decoder step. So this is a1 alpha. So the transformed vector, I'm just calling it as alpha 1. Okay, so alpha 1 is just a vector which is alpha 1 1, alpha 1 2, alpha 1 3, and alpha 1 4. Just think of these as just change numbers from a1, a11, a12, a13, and a14 with these numbers between 0 and 1, right? So um, so once we have alpha, this alpha vector, then we're gonna then we can already see something. Okay, so what we want to see is that um, you know these scores, these normalized scores, or sorry, these alphas, right? The probability values. Some probability values will be large, and some probability value will be small. Okay, and what is the number of probability values? The number of probability values is the number of inputs, right? So the input length for that sentence, okay, in this case 4. So here you can already see that alpha 1 1, for example, has a high probability, and alpha 1 2, alpha 1 3, alpha 1 4 have low probabilities, which means that maybe, I mean, this is just an interpretation, maybe that at this point when I'm trying to generate the output, the first word output, I need to pay more attention to the first hidden vector. Okay? That's just an interpretation. Now, if the distribution happened to be such that maybe there's more mass on A14, alpha 14, sorry, then maybe when we want to generate the first word, we want to pay more attention to this hidden vector. Okay? By default, without attention, by the way, we always, we don't pay attention to anything. So we had the last vector from which we generated the first hidden vector, from which we directly would have generated a distribution over the first word, right? So coming back to this example, we want to pay more attention to the first hidden vector. And how do we do that? Very simple idea. We just take an average. Okay? We just take an average over these hidden vectors weighted by the alpha values. Okay? So we take alpha 1 1 times this vector, alpha 1 2 times this vector. So it's a scalar times a vector is just the same vector. So we'll just add up these 4 vectors. Okay, we just take an average of these 4 vectors, average based on the alpha values that we have. Okay, it's just basically called a convex combination if folks are interested, but basically it's just an average of these hidden vectors averaged by the attention, the normalized attention scores. Okay, or attention scores which have been rescaled to be between 0 and 1. And so what we want to do is now this averaged guy z1, we want to use the z1 and the hidden vector that we got. Okay, we want to use both to somehow generate the first word. I can see, and you can already see if I have 2 vectors, I want to generate a distribution over words and therefore generate the first word, right? What can you do? You can do a very simple linear transformation, right? So, and that's exactly what we do. Okay? So we'll try to use this vector and this vector, concatenate them. Okay, so zt semicolon st just means, hey, put st next to zt, either before or after, and then do a transformation. Okay, do a transformation. Generally, I mean, since you have seen this several times, just do a transformation like a linear transformation. So zt say st, something like this, plus usual bias. Okay. So this is now a bunch of this is now a vector, some vector, right? And then from this vector, so let's just call it scores vector. I think my handwriting is not good today. Scores vector, and then again softmax it, and that softmaxed values are the probability distribution over your vocabulary. So all we've done is previously we would have not we would not have this, right? The vector at the top, which is this attended, averaged, attention weighted hidden vector. We would not have used that. We will directly go from the green hidden, first decoder's first RNN blocks hidden vector. We would directly transform it using a linear transformation to a scores vector, and again a softmax it to get a distribution over words, right? Instead of that, we are just tacking on, concatenating an extra vector. Okay, and that vector, um, is somehow retaining, for example, since you're trying to predict the first word, maybe it's saying, hey, let me use the first word's hidden vector to, do better in terms of the first word that I should predict. Okay, and maybe for the second word, maybe I need to focus on the second word, for example, and so on. So there's a mechanism for that to happen if such a you know such a such such a need arises. So as I said, for example, let's say we produce the first word. First word, as usual, just as before, decoder is going to be used as an input for the second step. Okay, for the second step, we'll use the previous hidden vector and the new hidden vector. We'll get a new hidden vector. Again, let's call this S2. Okay, but with S2, we want to again use that function. So again, H1, H2, H3, H4. Again, use, for example, H1 and H2 to produce a attention score, and then produce a normalized version of it, like between 0 and 1. Similarly, produce a score between S2 and H4, produce a score, and produce a normalized version of it. And this will be alpha 2. Okay? And attention weight corresponding to the second output that we want to care about. Now, once we have this alpha 2 vector, we'll just take alpha 2, 1 times the hidden vector, alpha 2, 2 times the second hidden vector, and so on, average. Okay, so it's a weighted average of the hidden H1, H2, H3, H4, weighted by these four numbers. Once we get this vector, we're going to use again this vector and this vector, and that's why you see these two arrows here, this arrow and this arrow together to get a distribution over words, from which again you can take the best, or you can you can think of beam search decoding, whatever. Okay. So that's how you generate vectors.
Professor, could you please explain it again? Just this he part, which you explained.
So what I'm trying to do is just forward pass. Okay, and as I said this before, right? So we're just trying to see, let's say, we're not worried about the parameters, training, and all that. Okay, we're just trying to figure out how to use the attention mechanism while spitting out the first word, the second word, the third word of translation. Okay, so this attention is only impacting the decoder part that you can see, right? So up to encoder, up to generating H1, H2, H3, H4 is just the calling of RNN, okay, or RNN units up to the 4 words. From this point onwards, we want to say, hey, now tell me how to generate the first word. Okay. And whether we generate the first word or second word, it's the same idea. So let's say in this slide, we're talking about generating the second word. Okay. Just so that, don't worry about the first word, don't get hung up on the first word aspect. It's the same computation. Okay. We know without attention that at any given step, we would have a hidden vector that will be passed to the next guy. Using that, I would also generate the first word generally. Okay. I would have a hidden vector, and I would use that to generate the word in the second time step, and so on, right?
Okay.
So, I mean, that was the usual decoder, right? Without any attention, I would have what I'm saying is without any attention, there'll be like the last hidden vector, let's say H4 is passed as an input. A start token is passed as input, right? And then somehow I need to produce an output, okay? A distribution over words, right? And hopefully the word which is the right word has the highest probability, right? So what is this block? This block is exactly the RNN block. And then you would pass another hidden vector, let's call it S1, okay, to the second word. So let's say this first word happens to be he, and then I'll have an RNN block, I'll pass he, I'll have S1, S2 will pass forward, and maybe a linear transformation of S2 gives you a distribution of again over words. Maybe again one of the words is hit. So this is the non-attention version. That's clear, right?
Yes, Professor, it is clear. The
Yeah. The
first.
non-attention version is clear. The only change that's happening is this arrow. When we're trying to produce an output, let's not just rely on um, let's not directly produce the output vector. Okay? What we're going to do is break this arrow somehow. Okay? Break this arrow in the sense that instead of using the hidden vector or whatever, the RNN's output directly to get to a vector, this is not a circle there. Yeah, this is the RNN, right? So we'll break these arrows, and the way what I'm trying to say is that um, instead of directly using the RNN's output, for example, let's say the same vanilla RNN produces the same output, right? It's really, although I say two outputs, it's really the same hidden vector, right?
Yeah.
Even for LSTM, it's actually the same hidden vector. It's just that the reason we are saying two outputs is because the hidden vector generally gets transformed linearly, and then that's the output. Okay, so that's why we just make a distinction that, hey, hidden vector being passed to the next unit, whereas a transformed version of the hidden vector, which generally happens with the output vector, is passed to as an output. Okay?
Yeah. Okay.
So what we're trying to say is that instead of directly going from hidden vector, let's say S1, which is the hidden vector there, directly going to get the word he, we're gonna use S1 and another vector, okay, and that's called Z1. Actually, here it's Z2, but that's called Z1. So we're gonna use S1 and Z1. Here, for example, to produce the second word, we're gonna use S2 and Z2. Okay, and what is this Z2? Z2 is this vector. So we're gonna use two vectors. So S1 and S2 were always present whenever we're doing decoder without attention. With attention, what we are adding is an extra vector. Okay, while producing the words, we want an extra vector Z1 and Z2.
Okay. And that Z1 is produced with the A's, which
Yeah.
is nothing but the probability distribution of H vectors using that green part. What is that green part again?
No, these are the hidden vectors of the decoder RNN. So
Decode.
see, so each of these square blocks here, squarish blocks,
Okay.
represents an RNN computation
Yeah.
unit.
Okay.
So all the circles in there are just it's like 4-dimensional hidden vector in this toy example.
Okay.
But so wait, so how are Z1, Z2, and maybe Z3, Z4? How are they produced? Exactly the same way. And let's actually do that maybe for Z3, because as I said, it doesn't matter whether you're at the beginning or whether you're trying to produce the first word or you're trying to produce the third word. For any word, you need to produce an extra
Z.
vector.
Yeah.
A
Got it.
vector that needs to be tacked on with S3, so that those two vectors together produce an output.
Okay.
Okay, produce a output, for example, a distribution of words, and therefore like the word me.
Okay.
How do we get Z3? Okay, whether it's Z3 or Z1 or Z2, it's all the same computation, same style of computation. Okay? But specifically for Z3, what we do is we produce these cores. Let's call it A31, A32, A33, A34. Okay. So what's the first index? First index is just saying, hey, this is the third word I want to decode. Okay, first index subscript. Okay, why I'm using 3 is there is because I want to produce a third word. Okay, because
Okay.
I'm using S3. Because I already have S3, I want to produce a third word.
Okay.
What is second index saying? Second index is just the index of the hidden output. Okay, so
Yeah.
hidden output is H1, H2, H3, H4.
Okay.
Therefore, A1, A2, A3, A4. Okay, second index is 1, 2, 3, 4. So what is A, let's say 3, 1, is just some function of H1 and S1. Sorry, H1 and S3.
Okay.
S3 is fixed always.
Yeah.
If I pass H1, then this is first index is A1. Sorry, the second index is 1. A32 is equal to the same function applied with H2 and
H2.
S3.
S3. Yeah.
Okay. If you want, you can flip these if you prefer S3 to be the first argument or whatever. It's the same thing. So you get these four numbers, okay? A33 and A34.
4.
These four numbers, whether you're talking about S3 or S2 or S1, is the same computation, except of course the input changes, right?
Yeah.
Same function being applied to get these four attention scores. Okay. From these attention scores, what we do is normalize softmax operation. So e to the power A31 divided by sum over e to the power A32 3j, j is equal to 1 to 4, right? The softmax operation you remember, right, from first session potentially.
Yes, Professor.
That's called alpha 3-1. Let's call it alpha 3-1. So that's this thing.
Okay. Okay.
This A31 is the small circles here, A31, A32. And the small box here, they are supposed to be alpha 3-1, alpha 3-2, because they're supposed to be probability distribution, okay, 0 to 1. So maybe, first it's a distribution over four, I guess, symbols, I guess, four support, it's basically a distribution which is trying to say which hidden vector is important now. That's literally what attention is about. Which hidden vector from this distribution, you can see that, hey, this third guy has a high, alpha 3 is high, which means that maybe H3 is kind of super important at this point. Make the, is important to make that prediction of the word me.
Okay.
So, but what do you do with this alpha? You just say, hey, alpha 3-1 times H1 plus alpha 3-2 times H2 plus alpha 3-3 times H3. Remember, this guy is high right here.
Yes.
Times H3 plus alpha 3-4 times H4. Sorry
Equal to
about my bad handwriting here, but this is exactly C1. Sorry, this is exactly C3.
Yeah.
Once you have the Z3, then you just concatenate and do a linear transformation and proceed forward. Okay. So this is the forward pass. Now you may ask, like, hey, why is it the case that this third guy is going to have a high probability, right? So high probability value. Like, why should it be the case? Okay, and it will be the case, because we are learning, right? So we are learning. So this f function that I said, this f may have its own parameters, and there's also parameters for the RNN. There's also parameters for the linear transformation, which is going from S3 and Z3 to Y hat. All these parameters are tuned such that it's able to ensure that you pick the right hidden vector to context, or some sort of pay attention to the right hidden vector to make the current prediction of the word. So it's just, we are post-hoc trying to we're post-hoc trying to justify why attention works, but why attention, this is how attention would happen. But why would it happen? It's because of training. Okay, we're training and setting the parameters such that if the third hidden vector is actually important while making this third word prediction, it will have a high value. Okay? If it is not the case, if the third hidden vector is not important, let's say it's always the case that the last hidden vector is the only thing that you need. You don't really care about any of these hidden vectors. Okay, then while training, it'll turn out the parameters of these objects like f and all the RNN parameters such that it will not pay any attention to any of these except for the last one. So the last one will always be high and everything else will be 0, for example. Or maybe everything is irrelevant or something, or there'll be equal distribution or whatever. Somehow, there need not be attention.
This example made sense for me. Thank you.
Yeah, I think the last sentence, don't worry about it, what I said. All I'm trying to say is that if attention was not important, it would not happen that such a distribution would happen. That's all I wanted to say.
Okay. All right.
And that all that is data driven through while doing that learning and backpropagation. The parameters are set such that if third vector happens to be important for producing the third word, a third input vector happens to be hidden vector happens to be important for the third word, it just will have a high attention score and so on. But yeah, that's what's happening. And these 4 slides are just showing, hey, Z1, Z2, Z3, Z4, how do we produce it? Exactly, so it's just showing these arrows, right? So H1 and S4 together will produce here, this is A41, and this guy will be alpha 41, and that weight will be multiplied with the hidden vector to produce Z4, in addition to all this weight times this vector, this weight times this vector, this weight times this vector. Same thing. Same as before. So I'm just saying that whether you produce he, hit, me, with, whatever the remaining words, it's all the same computation. Because same pattern of computation. Okay, I guess there are slides like this till you get hopefully the end token, and you can stop the translation. So the translation with this is this English sentence. and that's the mechanism of forward pass with an attention mechanism in place. Okay. Previously, you didn't have this extra mechanism. You would directly go from this green things to the word using, let's say, a linear transformation or something like that, using a fully connected layer basically to get to the scores, right? Um, yeah. Any questions here? I'll actually show another. I'll do a recap again for if people are we have time. Um, yeah, we do. So I'll do a quick recap again, but using the next module's slide deck. But before that, I want to mention one more minor thing, which is whatever we discussed pictorially in terms of if you really want to see the just a pseudocode in some sense, or like just a verbal description, is the following. At each decoding step T, what you do is you get first the decoding hidden state because you apply the RNN first, the RNN unit, you'll get you'll get the decoder's hidden state anyway. Okay. Now what you need to do is use the pre-computed hidden vectors of the input of the encoder, right? The H1, H2, H3, H capital T, or whatever is the number of whatever is the sentence length. You already have it. Using that, you compute a little p1 to a little capital T, right? So, that's exactly what we discussed, okay, using this f function. Once you do that, you do a softmax operation and then averaging. That will give you the z, right? We just saw this. And then you concatenate the z with the thing that you produce. So the z with the current decoder's hidden state. You concatenate just, one below the other. And then again, some transformation, maybe a linear transformation under softmax would give you a distribution over words. Okay, distribution over words is what you always wanted. Without the attention mechanism, you directly go from st to some y hat t, some distribution over words using, let's say, linear transformation, right? Fully connected layer, some fully connected layer. Instead of that, you're doing a few extra steps to get to that distribution over words. Okay. And the last thing I wanted to point out was that what is this function, right? So this function could be a parameterless function. It could be just a simple thing as, hey, you're giving me two vectors. If the two vectors dimensions are the same, let me just multiply them together. And that's my attention score. Okay, so you can define, sorry, this should be A. That could be my attention score. Or you can have, hey, let me actually have if the decoder's hidden vector and the encoder's hidden vector may not have the same dimension, for example. So then you can introduce an extra matrix in between to get to a single number. So remember, this f function is supposed to produce a single number, some number between minus infinity and infinity, right? So you can have a parametric function like this, or you can have a function which doesn't have parameters. Okay. Or you could even have something more complicated, which is, hey, you're giving me two vectors. Let me linearly transform them and then apply a tanh operation and then multiply with another vector to eventually get one number. Okay, so you can have some complicated function like this. Okay. So these all have names, but it's all, it's not like you will try to choose. You can certainly choose independently, but there's already prescriptions on which attention to use in many of the popular architectures. You kind of just stick with them. Okay, but these are all the choices that you can have for the f function. Uh, yeah. So any questions about the f function? So what I'm going to do is again now recap the same thing, but using a slightly different illustration. Okay. Just so that you see it in a recap in a slightly different illustration, it'll again click. Okay, so let me actually switch slides. Yeah, as I said, I'm going to do a quick recap. Quick recap of the attention mechanism that we've seen. And the reason I want to do a slightly different illustration is because we will kind of use the same type of illustration throughout the whole slide deck. So it's better to not switch between symbols and illustrations too much. So that's why I'll show the attention mechanism again for sequence to sequence or RNN models, this encoder decoder architecture. And then we'll jump into the new architecture for today. Again, to capture sequential relationship that came about in, I guess, 2017. Yeah, called transformer architecture. Okay, and we'll talk about how to use that in transfer learning. So this is, I guess, following the same idea that we saw in while we were working with CNNs. We saw towards the later part of CNNs, we saw how to use them in transfer learning, right? And you've also done an assignment 2 on this. So, and in particular, we look at, to do the transfer learning, we look at what is called BERT as a specific example model, pre-trained model. So let's actually get back again to attention. So I'll actually not spend time there. So again, neural machine translation, a slightly different sentence, but the idea is to view this whole process in terms of an encoding stage and a decoding stage. But now what I'll do is not split. I'll do it. I'll do it in the following way. First, I'll say, hey, I will talk about RNN units, okay, and then get into the details of the. We'll open up the RNN unit on the decoder side. Okay, so we'll do the opposite approach. So what I did in the previous 5 minutes was really talk about attention from the inside, and then talk about, hey, from there, how do we get a word? Here, let me tell you the translation from the top level. Hey, the translation happens like this. Then let's get into the attention decoder unit. So by the way, how many units will be there? It just depends on how long is a sentence. Okay, so here, for example, since there are only 3 words, there'll be 3 encoder units, RNN steps, basically. And how many decoder steps will be there? There will be those many depending on when you'll get the end token. Okay, or if you have a predetermined, hey, terminate after this many steps. So machine translation sequence model involves basically getting a hidden vector for each of these 3 words. So that's what's shown here. So actually, let me zoom in here. So hidden vector, which is passed to the next RNN unit, another hidden vector produced by the next RNN unit, and eventually, basically, at the end of the day, after encoding, you need to get 3 hidden vectors. So that, and once you get the 3 hidden vectors, you don't really need to think about encoder anymore. You just have 3 vectors. Okay. Now with those 3 vectors, your question is, how do I use those 3 vectors to produce words, or produce because you're talking about translation, how do we produce words in a way which is hopefully better than the vanilla encoder decoder architecture we've been talking about earlier. Okay. And for example, before we just recap how attention worked. So given these 3 hidden vectors and the RNN blocks, so on the RNN attention decoder RNN, which means that there's an attention mechanism inside, you produce the first word, and then you produce the second word, produce the third word, and hopefully you'll produce the fourth word, and then that's it. Okay, so that's it. So you somehow use these 3 vectors inside this block again and again and again to produce these 4 words. That's translation, right? Let's just recap what we just saw a few minutes ago. Now, if you split open, here's another view, another picture of the same thing that we saw. So in terms of steps, right? This just mixes both the verbal, the text that we saw 5 minutes ago, and also the um, illustration that we saw 5 minutes ago, which is what we do is we get the 3 vectors. Let's say in this case, in the previous example, there were only 3 input words, so 3 vectors. Okay, we get the 3 vectors. What we need to produce is a attention score for each of these vectors. Okay, so let's say 13, 9, and 9 are the 3, happen to be alpha 1, 1, alpha 1, 2, alpha 1, 3. Okay, 3 scores. Now we do a softmax operation to get numbers between 0 and 1. Okay, once we get the softmax operations, we multiply this times this vector, this times the second vector, this times the third vector. And that is shown by shading off, making the vectors with low values, because these values are low, those vectors are like kind of pretty much insignificant. Okay, and once you add these 3, therefore you'll get the summed up vector, which is that z1 that we had in the previous notation. Okay. At the same time, we also have the RNN decoder. The usual RNN block will also produce a hidden vector, right? So that's the decoder hidden vector or hidden state. Times step 4 just is because it's starting from input. There are 3 words of the input, and then we're trying to produce at the 4 times that we're producing the first word of the translation. Okay. And what we do, if you recall, we're just going to concatenate these 2 vectors and then do a linear transformation and then produce a distribution over our vocabulary as the from which we can sample or take a max to get the first translated word, right? So that's exactly shown here. So again, encoder produces 3 vectors. These are the 1, 2, and 3 vectors, vertical. Although it looks like a matrix, just think of the columns as the vectors, 3 vectors. As I said, from the 3 vectors, we produced a 1 z vector, right? Actually, here it's not called z, it's called c, but yeah, it's the same idea. And and what are these 3? These 3 are just the attention scores. Okay, so below they're just attention scores. These are the original vectors shaded by attention level. Okay, so high attention means it's not shaded out. If it's grayed out or whatever, it's become translucent. It means that the attention there is low, and you add them up. That's the attention vector. And as I said, you pick this vector, and the RNN itself produced an hidden vector. That vector you take, again, those 2 vectors you concatenate, do a linear transformation, right? A linear transformation, you get a score vector. Sorry, you get a score vector, and then do softmax operation. You get a distribution over words. Whichever word is the highest, that's the so whichever word has the highest probability, that's, for example, that's the word that you want to pick. Or you can do beam search, or you can do sampling, or whatever works. Greedy sampling. So greedy or beam search, those are the 2 things that we've seen, but that's what you do. Okay. So is that recap hopefully not confusing, and it's the same idea that we've seen before? Anybody has any questions? And those figures are just trying to show the same idea. So first attention, the same 3 vectors. First time the attention vector was this. Second time the attention vector happens to focus on the second hidden vector, and so it's a different vector. And then again concatenate the hidden vector at the decoder side with the Z2 in this case, or whatever, C5 here, do a transformation, get a distribution over words, and get your prediction. Okay. And the same thing. So any questions here before I talk about examples for same sequence attention, and then jump over to the next model?
So when we're looking at this, for instance, if we're looking at this in Python on more of a back-end perspective, what types of packages would we really implement, and what types of functions do you think we'd really use with these sequence-to-sequence functions with both encoding and decoding stages?
Oh, it's the same. It's basically what you've already seen in that example, right? nn.rnn, nn.embedding. Since you need to deal with words, and you've seen this in assignment 3, question 2, or even question 1, RNN to deal with that blocks, nn dot fully connected or linear layer, actually not FC, sorry. So you instantiate these 3. So we are using PyTorch at the backend side. Okay, so we have an init, right? Init function. You instantiate these 3 guys, but you also instantiate, since you have the let's say we are not really using we are using the simplest attention, where the f function for, let's say, hidden vector h1 and the state vector s1, or the notation in this slides are basically c4 and I think c4 and h4. It's the same idea. Is just h1 transpose s1, let's say, something like this. There's no parameter, let's say. Then that means that the attention part will not have any parameters. Okay, so which means that init would be just these 3. It's just that in the forward, okay, the forward function call, right? You produce the whole input sequence, right? The whole sentence, basically. Sentence is the input. Okay. Then what you do is you get the. So when you pass a sentence, all I'm saying is you pass the. Let's use this notation. Actually, this guy's notation. So when you pass a sentence, let's say the sentence is the 3-word sentence that we had here. I don't remember the exact sentence here. What is the sentence? Yeah, this French sentence here. Sorry, I had to go so many slides here. This French sentence. This is 3-word sentence. Okay, so that's what I mean by sentence over here in terms of software. Sorry, the scrolling here, but let's come back to where we were. Yeah. Yeah, forward sentence, then you basically have 3 words, right? X1, X2, and X3. Or word indices. From word indices, get to the word vectors. Let's call the word vectors X1, X2, X3. From the word vectors, if you pass it through RNN, you should be able to get H1, H2, and H3, right? And this, all this is, just standard. We saw this last time, right? That's, so when to produce these word vectors, we'll use the embedding. Produce this guy, we'll use RNN, right? So sorry, this is RNN. Yeah. So let's call this a encoder. Encoder class will have these 2 functions. Encoder, which is an extension of nn.module, will have these 2 functions, right? Now, just for the decoder, okay, same idea, but so I'll not write the init function. But for the forward, we'll have these input. Okay, H1, H2, H3 will be the input. Okay. Instead of sentence, it's just the encoded version, H1, H2, H3 is the sentence. Now, while doing the forward step, you want to do it instead of calling RNN like in a black box, you just have to do an extra attention step. So basically, you take so RNN step 1 will produce the let's say vector. Let me not use S. Let me use H. Okay, same as the notation here. Okay, here we're using H4 and H5, so I'm going to use the same notation. This produce the H4 by taking 1 step. Let me actually, yeah, take an RNN step. Actually, let me clean this guy as well. Take 1 step, you get H4. Now, what I'm saying is also compute C4, which is how do you compute C4? You know that it's basically H1. So you use so I'm given alpha. Let's call it. Sorry, I'm just going in a very so I hope everybody's clear, right? I'm just writing the encoder module with the 2 functions, decoder module with the 2 functions within the PyTorch based way. So I just need to write the forward. And here I'm just saying that C4 is just some complicated function. It's not a complicated function, but basically, for example, C4 will have some function of H1 comma H4, some function of H2 comma H4, some function of H3 comma H4. Based on these 3 guys, you take an average of H1, H2, H3, and that will be C4. Okay, some weighted average of sorry, I want to write that symbol either. It's just something times sorry, not something, but these 3 guys. I don't know what the symbol I've used here. I'm not using any symbol. So let's call this W1, W2, W3 is just W1 times H1 plus W2 times H2 plus W3 times H3. Now, once you have these 2, you just have to do the linear layer using H4 and C4 to produce your scores. Yeah, and from there you can do a softmax. I hope this is clear. I just did it as something in real time, but is it clear? So I guess the short answer is the software thing doesn't change. It's basically PyTorch modules. Only the decoder's description will change because now you have an extra attention block. Who asked this question? Is that clear?
Yes, and I did, and after you mapped it out, it makes a lot more sense.
Yeah, it's basically we are just seeing the illustration, but it's not like there's some crazy underlying package that you need to import which does this. Okay, it's exactly nn.modules that you have been extending from the base module. For example, for even CNNs, if you look at ResNet, if you use PyTorch pre-trained model ResNet 18, or whether you have used RNN in one of the assignment questions, this is how you do it, right? You just have a couple of functions that are needed, and the forward step, you just need to take care of attention explicitly, okay, like this, depending on what function you're using. That's all. So you need to write this, but of course there are pre-written ones in PyTorch that you can also use. Okay, so you don't have to explicitly write everything from scratch. People have already written this in PyTorch, using PyTorch as I guess the starting point, for example. Okay, so I mean, we can discuss that more about that because I think it's more relevant to the question 2 in assignment 3. Maybe we can discuss that after in the office hours, after the class hours. So now let's move forward. I just want to quickly mention how attention may look like using another illustration. The illustration is now, forget about the architecture, the underlying model. We just want to say, hey, this is the input sentence, let's say, these 3 words, and there's corresponding hidden vector, right? For every input, there's corresponding hidden vector. So let's call this, let's put them in orange. Let's put them in dark orange. And now I need to produce a output sentence in a different language. Okay. So what I'm trying to show here is that when I want to produce the word I, I'm just highlighting, I'm going to shade that cell the most. I'm going to always maintain 3 rows, okay, 3 rows corresponding to 3 input words. I'm going to highlight that hidden vector, which is the most important for me to produce the first word, for example. To produce the first word I, the most important hidden vector seems to be the hidden vector corresponding to the input, this input, right? Similarly, for the second word, it turns out that the first hidden vector and the third hidden vector are not really that important. The second hidden vector is important to produce the second word. And similarly, for the last word, it turns out the last hidden vector, and therefore the last input vector is important. Okay, so that's what you'll see. So how is the shading happening? This is exactly the weights, okay, the W1, W2, W3 that you saw in the pseudocode, or the alphas that we saw just 5 minutes ago is exactly this. So here the alphas are low, like since this is lightly shaded. Here the alpha is high. Yeah, that's all. This is just, and you can see that if it happens that if the 2 languages are such that the first word is supposed you literally can translate each word by itself, and in the target language it's the word sequence makes sense, then you should ideally see some sort of a diagonal structure. Okay, like while trying to predict the second word, you just need the second word, and predicting the third word, you just need the third word, right? But it's not always in the case. And here is a example where you roughly have a diagonal structure. Okay. This is again translation from French to, I guess, English. And you can see that in French, the specific, I guess, phrase and this specific phrase, they are said in reverse order. Okay, and so you can see that while trying to predict the word European, I'm paying attention not to this word, which is the next word in the sequence, but the word which is 2 words later. Okay, so by the way, this here in this figure, the lighter color means that input hidden vector has a higher, I guess, high, is being attended to, as in it has a higher alpha value. So here in this figure, light cell means that input word is important. So you can see that, for example, for the first word D, it turns out that the first input is important and none of the other inputs are important. Similarly, For end, it's just the end is important. And so for most words, it's basically just, the sentence structure is similar. So it's basically to predict the 10th word, you just need the 10th word's hidden vector basically. But it's just that, there's a slight change in the order in the source language. And so in the target language, it picks up that, hey, when I'm trying to predict European, I don't need to see the immediate, the like, the 1, 2, 3, fifth word, but I need to see the seventh word, for example. Okay. This is just a post hoc. Once you already trained a model, you can look at such diagrams just to get a sense of, hey, where is the attention being spent when I produce an output? Okay. So in that sense, they add some interpretability to, hey, which hidden vectors were important while producing a current word or something like that. Okay. Any questions? Yeah. If not, let's take a break, because the next we're gonna start a completely fresh take on modeling sequential relationship, and that's using transformer architecture. So let's take a break for 10 minutes and resume at 7:49. Okay, so welcome back. So I made a on-the-fly attempt to basically show what you probably have already seen, most of you, in assignment 3, question 2. The starting point was the sequence-to-sequence translation example, right? So there's a lot of pre-processing steps, and what I want to focus on is these two functions here, the decoder RNN and the encoder RNN. So this is exactly what I was trying to write earlier, by the way. So you have an embedding which goes from the symbols, the actual symbols in the sentence, the words in the sentence, to the vectors, the collection of vectors. If there are 4 words, then will be 4 vectors in this embedding object. And then you have a RNN block. Okay. So fully connected block is not needed here for encoder, because encoder is not outputting anything in the encoder decoder architecture, right? So in the forward step, you get the embedded vector, and that's it. You apply the in this case GRU, but it's just an RNN to get the hidden vectors basically. So here we are outputting both the output and the hidden, but you can just output, you can just output one. You can just look at the dimensions. You just need the hidden vectors basically. If there are 4 words, you just need the 4 hidden vectors, and that's what an object an object of this class will create. Okay, if you call the forward function. Now, in the decoder is where things get a little bit more interesting. You need an extra linear layer. That's because you're going from the hidden vector to a distribution or a vocabulary. And that's about it. And there's also a softmax function, but this is just a function. Okay, so you can always keep calling it instead of explicitly creating a object like this. But in the forward step, you can see that. Sorry, this is it's the usual decoder. So there's no. So in the forward step, you can see that from the output, like the first output, you're just creating. You're applying the out function, which is the linear function here. See, and then you're applying a softmax, and then you're getting the distribution over your vocabulary. Okay. Instead of this, the attention decoder, let's just focus on the forward step, is just computing attention weights. Okay, and this is exactly what we saw here. So you have the attention weights that you need to compute. Yeah, so you need to compute the attention weights. So here in the forward step, you should get the encoded input. Sorry, at the first step, you need to get the input from which you're creating the. So on the decoder side, first step, you need to get the. Okay. So So this is in the forward step. At any given time step, you need to take the current word, the current translated word. For example, we were doing from French to English. So let's say we've already translated 2 words of the English sentence. Then let's say, like for example, you're trying to decode, try to get a third word. Um, um, then basically that part should be this is captured in this input variable. So that still needs to be embedded. But you need to compute the attention weights. The A's and alphas are, I think that I use W's also in the annotation. So once you get the attention weights, you basically um, apply. I mean, here there's a specific function, so I didn't really spend time on the f function there. So I said f function could be as simple as hidden transpose. So the input hidden transpose the current RNN decoder state. But depending on if you use extra parameter, they will have their own linear layers, so basically their own parameters W and B, for example. So basically, you need to compute attention weights, and then your output is basically a concatenation of those two. So um, yeah, I don't want to do a real-time parsing of where how it's happening, but this is it. Okay, there's no extra package or no other extra software support needed. Any questions about this part? I was just trying to clarify earlier. There was a question about what else other than PyTorch, for example, is needed. There's nothing else. You just need to define that the computation that's going on, the weights times the hidden inputs, that concatenation to the current decoder state that has to happen. That's all. While computing the
Professor,
final.
what is dropout over there?
Dropout is an extra layer that was added. So if you recall dropout, so if you want to do dropout any layer, you just need to apply this extra step, right? So remember, dropout is this extra regularization that you can do at any layer, fully connected layer, typically. Yeah.
Okay.
So it's just a layer with a parameter, which is the dropout probability.
Okay.
Yeah, so this is all vectorized computation happening. That's why it's probably not that easy to grok. I mean, if you're looking at the first time, but like for example, what's unsqueeze versus squeeze, adding and removing dimensions. Those are all just to take care of these peripheral things like batch. If you have a batch and things like that. So like for example, dot view and so on. But at the end of the day, what we saw on paper earlier on the slide is exactly what's going on here. Okay. So, so let's, if there's time, we can discuss this at the end, but I really want to talk about transformer today. So let's move forward with that. Good. Okay. So, so there's a lot of parts. There are a lot of parts in transformer, but the core part is where we'll spend majority of the time. And there's some peripheral tricks. If you recall, even in CNN architecture, for example, the conv layer was the core, and then of course max, like a pool layer as well. But there's some extra tricks like batch normalization and dropout. Thanks for pointing that out. Similarly, in the transformer architecture, there's going to be some core building blocks, in particular the self-attention mechanism. And then we'll also address a couple of peripheral tricks that were there. For example, when transformer was proposed 4 years ago, less than 4 years ago, and so that's how we're gonna move forward now. Okay, but again, if you step back, this is a new architecture. It's not gonna look like RNN. So whatever you saw about RNNs, encoder decoder architecture, although we'll use the word encoder decoder as you'll see in the next couple of slides, you should park or keep aside or pause whatever you thought about for RNNs for now. Okay, I'll do a compare and contrast as we move along, but don't try to fit transformer architecture into your RNN worldview. Um, with that, so let's start. So transformer is a new model architecture again, which is useful for sequence modeling. Okay. Same, so which means that it's useful for capturing sequential relationships. Okay, and it also has an idea of attention. Okay, and in particular, it's called self-attention in this case. Okay, and is a core component of this model. So that's where we'll spend some time. And as I said, once we really go through that, then there will be a couple of more, I guess, peripheral tricks to completely describe the transformer architecture. So it's again the same application, variable length input, variable length output. Our go-to application has been for, I guess, a couple of weeks now, machine translation, right? So we'll go from the top, from top to bottom, in the sense that we'll unpack each block one by one. So if you're taking a bird's eye view, this is what happens. You have an input sentence. It goes through encoders, okay, which is a collection of encoders. Okay, this terminology is going to be using some words from the RNN stuff, but I will describe what encoder is here. Okay, and it's a little bit different. I would say it's a different beast than what you saw before. So there's going to be a bunch of encoders. There's going to be a bunch of decoders. Okay, it's plural, and some information is going to pass like this, and eventually you'll get a translated sentence. Okay, that's the high level view. Let's not worry about training. So of course there's going to be some parameters theta, some parameters, let's say theta encoders here, theta decoders here. There's going to be several parameters, and I'm going to tell you what the parameters are. How training is accomplished is exactly the same way. Once you describe this computational graph, you do a backprop and update the parameters given a batch of training data, the usual stuff that we've been seeing at the very beginning of this course, right? So, but we'll not talk about training and all that. Let's do a forward pass. Okay, which just means parameters are already given. Let's see how information flows through to get to our target, language translated sentence. So here is a view. Okay, we just broke down the encoders and decoders into explicit subblocks. Okay, and you can see that in this picture, okay, there are several encoders. Okay, 1, 2, 3, 4, 5, 6, 6 encoders, for example. But you can see that the number of words in my input is only 3. Okay, so the number of encoders has nothing to do with the number of words. So whether my input is a sentence of length 3, or whether it's a sentence of length 30, or a sentence of length 300, the number of encoders is going to be fixed, for example, in this illustration, to be 6. Okay? And you can also see another key point directly is that I'm saying input is the whole sentence itself. So I'm not saying input is this X0, X1, X2 business. Okay, so I mean, of course, there's going to be indexing, but it's not one step at a time. Okay, so first word, the second word, third word of the source language, source sentence, is input to the encoders, this collection, the sequence of encoders at the same time. Okay, so you need to have the full input. You're just passing it at one shot to an encoder, which passes to another encoder, which passes to another encoder, and so on, all the way to the top. And after this, after the last encoder, you'll have a bunch of vectors. Okay, maybe in fact, there's going to be 3 vectors. Okay? 3 vectors because there are 3 input vectors here. There are 3 input words here. Okay, those 3 vectors. Okay, 3 vectors. Okay, and the 3 vectors will each be passed to each of these. Again, I just in this illustration there are 6 decoders. Again, the number of decoders has nothing to do with the sentence length of the output. Okay, in this case, the sentence length of the output is 4. If it was 40, the number of decoders again fixed to be the same 6. Okay, so these 3 vectors somehow pass to each of these decoder blocks, and information is also passed across these decoder blocks. So you can think of although there's this split, and there seems like a time step type of a division between decoders, it's not the case. Okay, in the RNN case, there was each word being generated in a sequential way. Here, there is no, so some process is happening, but it's not like this decoder is trying to say what's the first word, second decoder is trying to say the second word. It's not the case at all. Okay, some information, okay, some encoders, as I said, produces 3 vectors. Those 3 vectors are passed to let's say, the bottommost decoder here. And from there onwards, some processing happens and you get a vector of words in one shot. Sorry, you get a collection of words in certain order in one shot. Okay, there's no sequential processing. So anyway, let's open up one thing at a time. So let's just and by the way, so you'll see that the encoder and decoder block are almost the same. Almost, there's one slight change, and so we'll spend the next few minutes really digging into. Let's open up one encoder, okay, one encoder unit, and really get into the details, and then we'll again zoom back out and complete the rest of the narrative. So one encoder unit has two subblocks. Okay, one block is, I guess, we've been talking about it since the first beginning of the course, a feed-forward layer. Okay. One block is, here we are saying feed-forward neural network. You just think of a feed-forward layer or a fully connected layer. The block that we have not seen, and it has the word attention attached to it, is this block. Okay, it's called self-attention, and we'll spend some time on this block. Okay, so you can see that there is when these arrows basically just represent some information, and generally in our case, information just means a collection of vectors. Okay, one vector or 10 vectors or whatever it is. In particular, as I'm already giving a teaser, the number of whatever is these blue arrows are, since I've highlighted them, if the input sentence happens to have 3 words, then these blue arrows will basically be 3 vectors each. Okay, so there's going to be basically 3 vectors going up, 3 vectors going up, 3 vectors coming out. Okay, and if these 3 vectors go to another encoder block, eventually there's going to be 3 vectors output. Okay, if the input length is 3, if the input length is 10, there's going to be 10 vectors going up. Okay, going up or whatever, going forward. Any questions at this point? We just talked about encoders and decoders as 2 parts of this neural machine translation example. And within encoders, there's going to be some collection, and within each encoder unit, there's going to be a feed-forward network and a self-attention unit. Yeah, module. Yeah. Okay, so next, I want to spend a couple of more points on encoder before we really open up these subblocks. First is that you saw a couple of encoders, right? So for example, here we saw 6 encoders. This guy, let's call it theta1 as the parameters. The self-attention will have some parameters. The new feed fully connected layer will have some parameters. This encoder, second guy, sorry, from the top, let's call it actually theta6. Call it theta1, theta2, 4, and theta5. The reason I'm indexing it 1, 2, 3, 4, 5 is explicitly to say that these parameters are not related to each other. Okay, so theta1 is a bunch of parameters related to the lowermost encoder unit. That has nothing to do with the parameters for the next encoder unit. Okay. Yeah, and important, again, I've mentioned it a couple of times already, all words will be input at the same time. So here I said if there is 3 words in the original input, then 3 words are passed, or some vectors corresponding to 3 words are passed everywhere at the same time. So there's no sequential aspect. There's no sequential computation, I would say. We do, of course, want to capture sequential relationships in the sentence, but that's actually captured using self-attention.
Professor, by this, do you mean that all the 3 words are passed to each and every encoder?
Yeah, not 3 words. Of course, the 3 words, for example, the word vectors are passed to the first encoder. But the first encoder always creates, if it gets 3 words, it'll produce three words as 3 vectors as output. If it gets 3 vectors as input, it'll produce 3 vectors as output.
Yes. Okay.
Those 3 vectors, these 3 vectors, the transformed ones from the first encoder, are passed to the second encoder. It's not the original input that's passed to the second encoder, but yeah. So if there are 3 words, 3 things pass to the first encoder, 3 things pass to the second encoder, 3 things pass to the third encoder, fourth encoder, and all that. It's the same thing. Is that clear? So
okay.
3 things pass, but it's from the previous encoder, not from the original.
Okay, got it. Yeah, thank you.
Okay, as I said, encoder and decoder almost look the same. So these 2 are the same. The self-attention is the same. There's an encoder-decoder attention. Okay, what is encoder-decoder attention? It's exactly the same as what we saw with the sequential. The RNN-based model. Encoder-decoder attention means you use some of the encoder's hidden vectors, and you use the decoder's hidden vector and merge them together using the transformation that we saw. Okay. Remember, if you have three vectors, three hidden vectors on the input and one current hidden vector, you just multiply each one of them. Not multiply, but it could be multiplication, it could be something else, to get the attention scores. With the attention scores, you get normalized versions, normalized probabilities. With the probabilities, you weigh the three input hidden vectors, and take an average. That average thing, those operations are happening here in this block. And we'll talk about it later. But all I'm trying to, at this slide, all I'm trying to say is that encoder and decoder almost look the same, except for an extra attention block, which we already seen. So what we've not seen is this. Okay, what is self-attention? How is it different? Okay, so we'll talk about it. We'll talk about more on these two first, and then talk about what's happening in the decoder. Okay, so let's get into the encoder. The encoder, as I said, has two parts. So let's say we're talking about the first encoder where the original input sequence is being passed, input sentence is being passed. Okay, so let's say this is sentence. Okay, then there's going to be some word vectors corresponding to those sentence, right? I mean, we can get them from pre-trained embeddings, or we can generate it from scratch by just calling nn.embedding and also training those embeddings together with the rest of the model, right? So let's say x1, x2, x3 are the three vector representations for the three words. Okay, all three words pass through self-attention. Self-attention block is also going to produce three intermediate vectors. Let's call it z1, z2, z3. And z1, z2, z3 are passed through the feed-forward layer, feed-forward module, submodule, and again, three vectors are produced. Okay, that's exactly what's happening. Um, yeah, so basically each word has its own path till the end. And like, for example, this is just one encoder. Let's say it's encoder 1. So the third word has its own vector by the end of this processing, right? And then the next encoder will get three inputs and therefore again produce three outputs. So every word, so basically each word has its own path throughout this 6 encoders, for example, that we saw in the illustration. Okay. So with that, let's actually get into the details, right? The details are basically, let's focus on this guy, okay, as well as this guy. This guy, so the one which is about feed-forward neural network. Let's say we have Z1 as for the first word and Z2 for the second word. Now I just changed the example to just 2 words instead of 3 words because 2 words is even simpler to describe than maintaining 3-word example. But nothing changes. Okay. So let's say there's, since there are 2 words, there's going to be just 2 words till the end of the encoder, right? So Z1 and Z2. What I'm trying to say is that for Z1, we will use some parameters. Let's call this. We don't want to keep using theta, but let's say some parameter w comma b, okay, was used to transform Z1 to some output. Let's call it R1. Okay, the same w comma b is used to also process Z2 to get R2. Okay, so but this is within the encoder number 1. Within the encoder number 1, all I'm saying is if there are 2 words, then for each of the 2 words, okay, each of the vectors corresponding vectors that were related to the 2 words, that's the same feed-forward transformation applies. The same linear transformation applies. Okay. But this is a minor point. But more importantly, what is happening here? Okay, what is happening in the bottom submodule? Okay, the self-attention module. The Z1 is produced not just using X1 but also using X2. Similarly, Z2 is produced somehow by not only using X1 but also X2. Okay, so this is how the self-attention is able to take into account that, hey, there's some words left and right, and they are relevant for me to encode or create a vector representation of this word, better and better vector representations of these words or hidden vectors for these words that will be useful for decoding. Okay, so that's the most important crucial thing, that Z1 certainly depends on the other words. So before, so what we'll do is, I guess, of course, clearly open this up, but Yeah. So, okay, actually, you know what, let me skip this only because I'll have the same slide in like 2 seconds. And so I'll describe that at that point. Okay. So let's actually open up the self-attention block. Okay. So I said there are two words for our example. Instead of 3 words, we just chose two sentence length to be 2. So 2 words. So let's start with their embeddings. That is clear, right? So we just need some vector representation for the words. That's fine. Now we're going to talk about what happens within one self-attention submodule. Okay. So from what we're going to do is from x1, x2, these are 2 vectors, input vectors. We're going to produce 3 vectors. Okay, 3 vectors. From each input vector, we're going to produce 3 related vectors. Okay, indexed by the same thing. X1 produces Q1, K1, and V1. Similarly, X2 produces Q2, K2, and V2. Get 3 vectors. How do you get 3 vectors? Just do some linear transformation. Okay, you know, so if you have a vector, you want to produce three vectors, possibly of smaller dimension. For example, let's say 64. Let's say the original one is 512 dimension. Okay, some higher length, some length. Let's say 512. You want to get another vector, you just do a linear transformation, right? So basically what I'm saying is, like, for example, Q1 is some WQ times X1, some linear transformation, right? You multiply a matrix, you get another vector. So you can get 3 vectors, right? You get 3 vectors. Now what you're going to do is somehow use these 3 vectors each for each of the 2 words that we have to produce Z1 and Z2. Remember, the self-attention model is producing Z1 and Z2. And somehow we need to make Z1 dependent on not just X1, but also X2. Similarly, Z2, we want to make dependent on X1 as well as X2. Okay, these green guys. So how do we do that? Here's the process. And I'm just describing very mechanically what's going on inside the attention block. We'll talk about the interpretation of why this may help in a second. Okay, so let's talk about the mechanical computation first. So as I said, we'll get the 3 vectors from each of the input vector x1 and x2. So what we'll do is first compute scores. Okay, so we'll just call them scores. The scores are going to be, take the Q vector. It's called, okay, by the way, Q, K, and V correspond to query vector, key vector, and value vector. Okay. So what we're going to do is use Q query vector for the first word and multiply it with the key vector for the first word as well as the key vector for the second word. Okay. So what I'm trying to do, so in this, I guess, in this slide, my goal is to get to Z1. Okay. I'm only going to talk about getting to Z1, and we'll see that the computation for Z2 is different, is similar, sorry. Okay. So to get to Z1, what we're going to do is take the query vector for the first word, multiply it with the key vector for every other word, including its own word. So I'll multiply with my key vector. I'll also multiply with the other key vector. So if there was one more word, there'll be Q1 times K3. If there was one more word, it'll be Q1 times K4. Okay. So the vector is vector times vector. It should be same dimension, hopefully. And so it's just a number. Okay. So U transpose V. Okay. Once you have the score vectors, what we want to get is a normalized version of these numbers, right? If we get a score vector like 2 numbers, we somehow want to get them back to a number between 0 and 1. Okay, so I got 2 scores. Okay. I got 2 scores because there were 2 words. If I had 10 words, I'll have 10 scores. Okay, there's some minor detail about dividing by some constant, but it's a minor detail. It's specific to the transformer implementation that that was defined, but it's just some scaling. Okay, it's just divide by something, 10. In this case, divide by 8 here, but doesn't matter. Some constant scale down of the score value. Then you just apply softmax, and we know what softmax is. Given scores, we always know how to do softmax operation, and so we get the softmax scores. Okay. So what have we used so far? We have used Q1, K1, and K2 in this example. If there were K3, K4, K5, we would also use them. So we have used the query for this first word and the keys for everybody else. Okay. Now what is left to use is V1 and V2. Right? How do we use V1 and V2? Since we have the softmax values, we're just gonna do a weighted average. Okay. So we'll take the softmax value times the current value vector, softmax value times the value vector for the second word. If there was another softmax value times the value vector for the third word, and so on, if there were others. And we'll just sum them up, average them. It's very similar to the attention mechanism we saw earlier. Okay. So that's going to be the Z1 vector. So somehow Z1 vector is basically saying, hey, the vector that I want to show for this original word thinking, should it, should it use the value vectors? Should it depend on, for example, if instead of the score being 88.88 here and 0.12 here, if it was the opposite, then the second value vector would be the one which would be highly dominant in the Z1 value. So in the Z1 vector, right? Somehow, so that's actually capturing relationship between words. Okay. And of course, what are the parameters? These are the parameters. These are the parameters. Okay? They have to be trained such that the signals are picked up appropriately. So we just saw how to compute Z1. Similarly, Z2 is again computed using the Q2 query vector for the second word, and key 1, key 2, because there are only 2 words. If there are key 3, key 4, key 5, they'll all be used to compute scores and therefore softmax values. And then you again do a weighted average of the value vectors. Very similar. Okay. The computation that I just showed here in this here can be done in a vectorized manner. Okay, and the vectorized manner is you can literally multiply, since they have 2 words, I can have X matrix which has 2 rows. Okay, I can just multiply with WQ to get the Q matrix, where the first row corresponds to the query for the first word and second row corresponds to the query for the second word. Okay, if there were more words, there'll be more rows and there'll be more query vectors. Okay, similarly, you can do the key matrix. You can get the value matrix. It's just a vectorized. There's nothing going on here. So if you didn't follow this part, don't worry about it. It's just it's the same computation that we saw in the previous slide. Further, the rest of the computations, remember we had the query matrix. So we have the query vector. We want to multiply it with each one of the key vectors, get the scores, somehow apply a softmax operation, and then take an average over the value vectors, right? The whole thing can actually be just written as some, in a vectorized way, in some sort of a compact way like this. So you have the Q matrix. You just multiply with something called you just multiply with the transpose of the key matrix. Okay. If you do that, you'll actually get scores for all pairs of, for all, you'll get scores for each word and every pair of words. Okay, so basically, if there are 2 words, then you'll get scores, and you'll get 4 scores basically. Okay, so and then you can just multiply with the value matrix. So basically what I'm trying to say in this slide is exactly that this expanded computation that I showed here, like explicitly, hey, get the QKV, get the score, divide by something, apply softmax, multiply with value, take an average. This whole thing can be just shown as one computation here. Okay, just think of it as a shorthand notation for those sequence of steps that we saw. Any question up to this point of what is, what is the mechanical steps in self-attention? So I'm going to talk about interpretation of what self-attention is trying to buy us in the next couple of slides. So yeah, so I'll actually wait a couple of more slides for interpretation, because since we already understand, hey, how do I get to these 2 vectors? Remember, if you remember again the encoder block, inside encoder block, there's a self-attention block. And if there are 2 words, then it has to be 2 vectors, okay? Z1, Z2. Let's say Z1, this is Z2. If there were 2 inputs, there has to be 2 outputs of the self-attention block, right? Self-attention block, right? Now, what we want to show is that at least the original transformer architecture, what those researchers did is do this computation many times in parallel. Okay, do this computation many times in parallel, and that computation or that module or that computation block is called multi-headed attention. Okay, it's just self-attention, but if you do it 8 times, but everything in parallel, okay, then I mean everything in parallel, but each instance, each I guess version, each of these parallel guys will have their own parameters. Okay, so and let's actually expand that out. Multi-head attention is about doing multiple attention computations in parallel. Okay, multiple attention computations in parallel, where each attention computation is exactly same as what we saw earlier. Okay, and why are we doing this? I guess the zeroth order reason is it's empirically seems to work well. Okay, really capture the sentence structure while doing, for example, translation or language modeling. Okay, and actually, let me come back to the slide that I skipped. Yeah. So what is attention? So I want to come back to the slide just because since we saw single-headed attention or just self-attention, what is attention trying to do? So for example, if I have so many words, right? So I don't know how many so many words or tokens that we have here. Let's say these are the tokens that we have at the input. Okay. For each word, as I said, there's going to be a corresponding, if it passes through the attention submodule, there's going to be one vector for each word, right? So let's focus on the word it. Okay, let's focus on the word it. This word, what we're trying to show is that, and of course at the input, there's going to be word vector for each of the words, right? I mean, if you say exactly at the input, there's going to be a word vector. If it's, let's say, the third encoder, there's going to be some vector corresponding to each word, right? What it's trying to show is that this attention mechanism, what it's trying to do is that for each word, it's trying to attend words related to it, as in like make the word representation, like for example, the representation of the word it is trying to make it dependent on what words are related to it. For example, it, for example, could be related to the word animal, right? It could represent, the information about, hey, it's about this animal word, okay? And that's happening through these attention weights, okay? These scores or normalized scores that we're computing. The scores will be high, and so here the color, this darker color means that the scores are high, and this lighter color means that they're not related. And so you're taking an average of all these vectors, the value vectors for each of these words. You're taking an average based on these attention scores. Okay, so the attention scores are somehow trying to get better and better representation for each word, okay, depending on how it's related to the other words in the sentence. Okay, that's what's happening with attention. Any questions here? Okay, so let's actually go to multi-headed attention. I just wanted to mention that before we talk about multi-headed attention. As I said, multi-headed attention is just computing self-attention several times. But if you compute it 2 times, what's the difference? The second time when you compute, it will have a different bunch of parameters. WQ, WK, WV that you saw. There'll be different matrices. That's all. Because they're different matrices, your Z1, Z2 will be different if you use a different bunch of matrices, right? So that's kind of clear. So, but you start with the same vector. So same 2 vectors. Let's say x1, x2. Because the matrices are different. Let's say in this illustration there are 2 attention. I guess these multiple versions are called attention heads. Okay, attention head 0, attention head 1, attention head 2, and so on. And so each one will produce a Z1, Z2 pair, right? Since there are 2 words in since there are 2 words in the input. If there were 10 words in input, there will be Z1, Z2, Z10 for the first attention head. There will be Z1, Z2, Z3, Z4, Z10 for the second attention head. Okay. Now, I mean, that's what I guess I showed here. So in particular, the original architecture had eight attention heads. So that's why here in this illustration, there's attention head 0 to attention head 7. Okay, there are 8 attention heads. So we got Z1, Z2 all the way to Z7, 0, Z0 all the way to Z7. Okay, but you didn't want 7. So, and what's the motivation for this is that the model can, this is empirically validated. That's one zeroth order motivation in the sense that it's turned out to be important component of improving language models in 2017, 18, and so it's empirically works really well in terms of capturing language models, and so therefore subsequent other NLP tasks. But also the intuition is that with multiple attention heads, we can, hey, if you think of the word, let's say the 10 word sentence like we saw earlier, right? In the example, there was a word it. Okay, maybe it's related to animal. Okay, maybe it's also should depend on some other word, in that sentence, that 20 word sentence that we had. Okay, so each attention head could capture multiple such representations. Okay, because maybe a word is related to not is may not be just related to an animal. It may be related to some other words as well. Of course, a single attention head will also capture that by just ensuring that the two scores are high for two words which are related to the same word. But you can also have multiple such attention heads capture this as well. Okay. And also because these W's are different, you somehow get like different embeddings or different Z's from the same starting point, and that helps better capture the representation of the original sentence. Okay. So those are, I guess, a little bit intuitive explanations, but eventually, I mean, what matters is that empirically having multiple attentions in parallel at any given encoder's self-attention module seems to provide really good benefit in terms of performance. Okay, for example, in language modeling and other tasks. So in that sense, let's say we produced Z1, Z0 to Z7, but we still need to pass one vector per word to, let's say, the next submodule, which is the fully connected module, right? How do we pass one vector when we have seven vectors? For example, for the first word, we have 7 vectors, right? Even for the second word, we have 7 vectors. Oh, sorry, 8 vectors. How do we merge it? And the idea is very simple, right? You concatenate these vectors. Okay. For example, let's say focus on the first word. You concatenate this vector. So 7 times you get a vector which is 7 times the length of the vector that you should have gotten. So what you do is do a simple linear transformation. Okay, so let's call this linear transformation parameter WO. Okay, that takes this. When I keep saying 7, it's 8. Okay, 0 to 7, so 8. So this 8 times long vector, you somehow apply a linear transformation such that the output is only the length that you should have gotten. Okay, which is, for example, let's say 64 or 512 or whatever it is. Okay, and similarly, you can apply with every word. Since there are 2 words, that's why in this illustration there are 2 such shrunk vectors. Okay, so that's how you go from multi-headed parallel computation, multi-heads, to again just 1 word per vector. Sorry, one vector per word. Okay, of the right dimension. And that's exactly shown here. So everything is shown here. Let's say you had 3 such attention heads. So these you actually have 8, but here in illustration we put an ellipsis here, and so these are the parameters. You get the query key and value vectors. You get the Z's. From the Z's, using a linear transformation, you get 1 vector per word. Okay, so if the 10 words, there should be 10 such vectors. Okay. That's because there's only these many words in the input. And yeah, and so in the first encoder, of course, you need to produce the embeddings of the words You need to either do NN.embedding, or you need to use pre-trained embeddings to get the embeddings of the words. For the, like, when we look at the second encoder, we need to provide the input from the previous encoder, and that's just we're just calling it the R vectors here. Okay, because if you recall, the final output in the encoder is, we're just using the notation R1, R2. Okay? And if it was the first encoder, the input is going to be X1, X2. But if it's the second encoder, right? Second encoder will have R1, R2 output input, and also R1, R2, maybe the next one, the client, as the output. Okay. So within encoder, what we've discussed so far is just the self-attention block. We have not yet fully discussed the fully connected block, but fully connected block is not complicated, right? We have seen several times a fully connected layer, so it should not be a problem. So if you see the multi-headed attention, again, to interpret like what's happening, here's an example sentence, okay? And we are seeing just two heads, okay? Two heads. So why we're seeing, why do I say we are seeing two heads? Because there are two rows, two columns here, rows corresponding to words. So we need, if, whatever is the number of words here, the same number of vectors should be produced, okay? And we are looking at the vector for the word it, okay? In one head, let's say the orange one, you can see that the vector has high scores for this part, okay? High scores for the and animal, for example. Okay? Similarly, in a different head, which is this green head, this word it has a high score for the word tired, or whatever. Okay? So you can see that different attention heads could capture different word relationships. That this word it should be influenced by the word animal, or the word its representation should be influenced by the word tired. Okay, so that's the, I guess, use of multi-threaded attention. But of course, this is a illustrative example. This is not like, for example, if you look at all the 8 attention heads, it's hard to interpret what each of the attention heads is doing. So the orange and the green are from before, but the other heads, are not very interpretable. But it turns out that having these multi-headed attention really helps in practice. Okay. Um, yeah. Any question about this part? Wow, I'm already feeling tired. Um, okay, so what we'll do is pick back up from where we stopped here. So just to conclude, we in the transformer architecture, it has encoders and decoders. They are not the same as the RNN architecture's encoder-decoder architecture. Okay, and within an encoder-decoder in a transformer architecture, they're almost the same. There's an extra self, encoder-decoder attention in the decoder. So what we're trying to do now is just open the encoder box, encoder unit, and look at what's going on inside. And within that, we saw there's something called a self-attention submodule. And what we've done so far is really understand the self-attention module. Okay, this is the end. Okay, there's nothing else to talk about in self-attention. But hopefully after this class and hopefully before next week, you can just revise, hey, we saw self-attention for transformers, and we saw the usual attention mechanism for the encoder-decoder architecture for RNN. They have some similarities, but they're also different. Okay. Hopefully you can compare and contrast. And next time we'll talk about the remaining peripheral things related to the transformer architecture that completes the architecture. Okay, so this is the core block. There are a few more things that complete the picture of a transformer architecture that lets you do, for example, language modeling, translation, and so on. Okay, so with that, let me stop here. I apologize for going over time, but I hope you have a good day. Good rest of the week. I'll pause here. And folks who have questions, do stay back. I'm sure there are questions given the first time you're seeing this. So do stay back and ask me questions. Thank you.